So the topic of this talk is inside Spirit X3. Quick agenda. We'll have a quick overview. I don't think I'll have enough time to go through that in detail, but most of it I'm guessing that you already know. So we'll go through that very quickly. Parser combinators too, we'll go through that very quickly. Then we'll go to start building a toy Spirit X3. For that exercise, the hope is that we'll have a simple example of Spirit. That way, you'll be able to understand the concepts behind the library. And then we'll go to a walkthrough of the actual Spirit library, X3 library. We'll go through some of, not all of course, but some of the important parts of the code. That way you have a deeper understanding of how Spirit X3 works. Okay, so I'm guessing that I don't have to go through all this. I'm assuming that you already know this, what Spirit is. Maybe a quick question. Who among you don't know Spirit yet? Okay, so do you want me to go to this slide, or is it okay to skip this slide? Okay, now Spirit X3. What is Spirit X3? It's an experimental version of Spirit. It's using lots of features of C++11. It's hackable. At least that's what I intend it to be. And it has a very simple design. Compared to V2, X3 will be so much more simpler to understand. It has minimal code base and dependencies. So it's still relying on MPL. I can't live without MPL. Although I tried to find a way to have some minimal type list mechanisms. It just not good enough. So why reinvent the wheel? So you have MPL. Fusion, same. I can't live without Fusion. So that's it. So Fusion will have to be there. I tried as much as I can with Spirit X2 to minimize the dependencies, but there are really things that I can't live without. How about Phoenix? Okay, Phoenix, Phoenix is my baby, literally and figuratively. So I'm quite attached to it. But with Spirit X3, I'm not relying on it anymore. I'm not depending on Phoenix anymore. Particularly because we have C++11 Lambda. And because when Spirit 2 came out, the focus was not on semantic actions anymore. The focus was more on attributes and attribute handling. We'll see more about that as we go through the slides. Okay, how about Proto? This will be a contentious one. I know it will be, I might sound, sacrilegious to many of you if I say that I won't be depending on Proto anymore. Or at the very least, I will sound uncool because, well, Proto is a cool library. But I'm keeping an open mind. And since I heard Eric's talk on Proto for C++11, I am quite amazed. But the bottom line is that, well, one word, cost. Unfortunately, Proto is quite expensive at compile time. And for two things, why I can't justify the cost, two things. One, the expression template part of the library amounts to less than 5% of the total code base. So it's a small part. And number two, well, I love writing expression template code. I love writing the overloads. I love designing the expression trees. I love doing that. And I will show that it's easy to do. And for the purpose of Spirit, I would say that at some point, when you have a simple expression template grammar, it's best to do it hand-coded. That's my opinion. Anyway, so because of that, because we have minimal code-based dependencies and we have a simpler design, we'll have faster compile times. And one of the goals, I skipped over that, we'll have, one of the intent is to have better error handling as well. Yes, Michael? No, I can't live without MPL. I can't live, okay, repeat the question. Michael is asking if I have to get rid of all of this to minimize the dependencies. So the answer is, I can't get rid of MPL, I can't get rid of Fusion. I can live without Phoenix because we have C++11. And I can live without Proto because, well, I enjoy writing the expression template code. And unfortunately, the cost of Phoenix, both Phoenix and Proto, is a bit too steep. And I want to minimize the compilation time. That's one of the strongest arguments against using Spirit. The compilation time is too, well, you know what I mean, I guess. Okay. To give you a hint, I've ported the Calc4 CPP example from version V2, and this is the compile time that I'm getting. This is using a virtual machine. Unvirtualized, this will be so much faster. But you can see that it's twice faster. Okay, so I'm just going to go through this very quickly. What's a parser combinator? Well, a parser is a function. An example is a character parser. Another example is a numeric parser. Those are all functions. Parser can be composed to form higher order parser functions. So for example, you have a sequence parser accepting two parsers, the left-hand side and the right-hand side. You form that into an aggregate, which is a sequence parser. Such a higher order parser function is called a parser combinator in the function programming domain. A parser combinator accepts several parsers as input and returns a composite parser as a result. Here's how it is as an example. So you compose small parsers to have more complex parsers. Okay, so here are a couple of examples. We have primitives and the pseudocode below it. Sequences, match this and this in sequence. Alternatives, match F1 and F2 in sequence. Modifiers, you have the clean, plus, etc. For example, the example there is the clean. So it's matching 0 or more of F. So it's invoking F 0 or more times until it fails. And it returns true because you have 0 or more match. Okay, so all of this is based on a language, which is the parsing expression grammar. It's a formal grammar for describing formal languages in terms of a set of rules to recognize strings of this language. It doesn't require tokenization stage. You don't need a lexer, but of course you can use a lexer if you want. And in fact, Spirit version 2 has a lexer. Unlike eBNF, PEGs are not ambiguous, exactly one valid parse tree for each PEG. any PEG can be represented as a recursive descent parser. So there's a one-to-one correspondence. It has a different interpretation as eBNF. Most particularly, we have greedy loops. So it will match as much as, it will try to parse as much as it can without regard for the tail. You have alternatives, which is a first come, first serve basis. So the first one that matches wins. Yes, question?
When you say version 2 had Alexa, are you implying version 3 doesn't have Alexa?
Not yet at this time. So at this time, what's ported is the key part. If you, sorry, repeat the question. David was asking if X3 will have Alexa or will not have Alexa. Is that the question? So the answer is that X3 will have Alexa in due time. It's not yet ported. So what we have is the parser, is the PEG parser portion. We don't have Karma yet, which is the output generation. We don't have the Lexer yet. So it's just PEG at this time, the key part of Spirit. Okay, here's an example. And I guess that's just reiterating what's been mentioned in the previous slide. And here's how it happens. So you can see the diagrams here, how the small parsers, all of these are parsers, and they are combined to form higher order parsers. So you have the integer, which is a primitive parser, and you have these literals. This is a non-terminal, which is also a parser, and then another parser. Then you can combine these three to form a sequence, following that, and then you combine all that to form an alternative. So this thing over here represents that PEG expression over there. And this is the pseudocode generated by Spirit based on the composition of the parsers. Okay, so that was quick. Let's build the Toy Spirit X3. Let's see how it goes. Hopefully, at the end of this exercise, you'll have a deeper understanding of how Spirit works. And the point that I'm trying to get across is that it is easy. It is easy to understand. And my purpose is that I need people to contribute to the code. Okay, so we start with the parser base class. This is the root of the expression template 3. So I'm pretty sure you know this, how this works. This is the canonical CRTP class. I'm just wanting to mention here that it's in namespace Boost Spirit X3. All of the components that I will go through in the subsequent slides, I will not be writing that namespace. So everything is under its Spirit namespace X3. Okay, so that's a typical CRTP class, and all derived parsers inherit from that. So that's the root of all parsers. All derived parsers shall have a parse member function with that signature. It's a template. You have the iterators, iterator range, first, last, pointing to the input stream. Those are forward iterators. And you have the context. This is a very important concept that I will discuss in the next slides. So these are the post conditions for the parse member function. Upon return from a parser, from a parse, the following post conditions should hold. First, on a successful match, first, the first iterator is positioned one past the last matching character. You can notice that it's passed by reference. So the parser moves that iterator to one past the last position that's matching. On a failed match, first is restored. So that's quite simple to understand. I guess I don't have to explain this part, but it just happens that because Spirit can be used without a lexer, there's what we call the skip parser. And the skip parser skips the trailing spaces before parsing. So this happens for all the primitive parsers. For example, you have the car parser and you have the numeric parser. Before it starts doing its business, it will try to skip the white spaces before it, defined by the skip parser. So what this says is that there will be no post skips, only pre skips. Okay, so to show you how easy it is, this is actually the complete parser, the complete character parser. So it's a simple class, one member variable, which is the car. It's templated, but it's a templated by the car type, can be a car or W car T. And here's what's important, the parse function. So I guess I don't have to explain what this does. So it tries to match the character that you have with what's in the input and advances the iterator appropriately and returns false if there's no match. So it's... Yes, you see that the iterator is not incremented only if you have a match. This part here. So it returns true, the iterator is positioned one after. So in this case, the iterator is not moved. Okay, now here's the ET. How can it be easier? So just if you want a car parser, you'll have just to create a car parser using that function. So that function is the ET expression template for that particular parser. For those who have used Spirit and Spirit V2, the car underscore should be quite familiar. Okay, now let's move on to a composite parser. This is the sequence parser, and that's it. It fits in one slide. Yes? Oh, okay. How do I match any character? Well, yes. This is Toy Spirit X3. And for the purpose of explanation, I simplified a lot. But the actual parser, the actual car parser, will be a little bit more complex than that. But for what I'm trying to get across is the simplicity of the design to get to have you get the idea of how everything works. And actually, the actual code is not so much more complex than what you have here. Okay, so here's the sequence parser. It's templated. The left and the right are assumed to be parsers. It's inheriting from the parser base class, passing its type, you know, the CRTP technique. in its constructor, it's taking in the left and right parsers. So it's composing. So you have the left and right composed from that one. And you have the main parse function, which I think should be immediately understandable to all of you guys. So it tries the first left. If not, it'll return immediately, return false immediately because of short circuiting. If this is successful, the first parse iterator will be positioned appropriately for the right parser to be tried. So that's actually working code in our toy parser. And here's the expression template for that parser. So we have an overload. Sorry, where's that? Oh, there you go. Overload for the right shift operator. And then it's taking in a parser for the left operand and another parser for the right operand. And it composes. As simple as that. So here's another composite parser. You can see it fits in one slide. It's very small. I like small classes. I like small and one-purpose classes. And this is another example of the composite parser. So it's the same as the sequence parser, but the logic is different. This is how alternatives are parsed. And there's an appropriate expression template overload for the alternative parser. Same as before, you have the right-hand side and the left-hand side parsers. You combine that and create a composite parser. Okay so far? Great. Okay, now here's one thing that's very nice with C++ 11. You have auto. And with auto, you can create, with just the parsers that we have, we can have simple rules like this, which works. For example, this is a sequence of A followed by B followed by C, and that works. It's a sequence parser, sequence of a sequence actually, and that works. Same thing with this one. You have A or B followed by C. So you have the expression template, and that creates a composite parser, and you can call its parse member function, and it does the right thing. So it's very tight, it's very small. Even with that, you can have small parsers. The code is very tight, the code is very lean. It does what it's supposed to do. And you don't have a code bloat at all, and it's very simple. So what I'm trying to do is separate this core parsers, the things that you really need, into a very small minimal subset for people to use, so that you don't have to have all this whole set of bag of parsers. You have a minimal set to play around with. This is especially good for writing small micro parsers. For example, say for example, you'd like to parse a complex number. So that's how you do it. Okay, so but how about recursion? Say I want to parse these inputs, x, a followed by x, AAX, and any number of x, a terminated by x. So in other words, I want 0 or more a's followed by x. Okay, you can do that using the clean star, but for this purpose of the toy parser, we don't have this clean star yet. So I'd like to introduce how rules are implemented using X-tree, and this is the way to explain it. So we want to have something that can recurse. Can we do that using auto only? Here's a try. And then that. But can you see the problem? Yeah, dependency. So x depends on ax, and ax depends on x. That's a problem. So that's why we need rules. We need rules that can recurse. Auto is very powerful as it is, but you can't have recursive auto definitions. Okay, non-terminals. The rule is a polymorphic parser that acts as a name placeholder capturing the behavior of a PEG expression assigned to it. So you have a right-hand side expression. You want to name it, you assign it to a rule. It's something like what we did a while ago using auto, but this time we can do recursion. But how can we do that? Okay. Naming a PEG expression allows it to be referenced later and makes it possible for the rule to call itself. Obviously, you can't do that with auto because you can't have the name of the variable be on the right-hand side of the equation. That's not possible. So this is one of the most important mechanisms and the reason behind the word recursive in the recursive descent parsing. Okay, in Spirit in classic style, we have Spirit 2 and we have the classic Spirit. We were using abstract type erased functions. In Spirit Classic, we used virtual functions. And in Boost, in Spirit 2, we are using Boost or standard functions. So in a way, we are hiding the types using type erasure. So here's an example using Spirit 2. So same as example as before, implemented for Spirit 2. So when you assign this expression to x, it will hold it as a boost function. Same thing with ax. But there are problems with type erasure. All template parameters should be known beforehand. Hence, the rule needs to know the scanner type in Classic Spirit, if you remember Classic Spirit. And in V2, you need to know the iterator type. And that is why in the previous slide, you specify the iterator type for the rule. And I'm not even mentioning about the context. So that's a big problem that we have because you'll have to always specify the types if you use type erasure. Okay, code bloat, that's a big problem with virtual functions as well because all virtual functions are instantiated, always, even if you don't use it. And so it prevents optimizations. So the virtual function is an opaque wall. In general, compilers cannot see beyond that wall and cannot perform optimizations. Well, there's link time optimization, but I don't want to digress. Okay, so X3 style. X3 style does not use the boost function, does not use type erasure, does not use virtual functions. It is inspired by the Spirit Classic subrules, well, taken to the next level with the help of C++11. The big difference is that in V2 and in Classic, the subrules are compile time monsters relying on expression templates. So this time with X3, I implemented it a bit differently to make it more easier to compile. Okay, so let's go back to the context. The context is an important component of Spirit X3. We have the context in Spirit X2 as well, but it's not used quite as extensively as we do it with X3. So what is the context? The context allows functions to efficiently access data from other stack frames. So you have recursive functions. You have this function calling this function, calling this function. I'd like to be able to get context information from this outer function in this inner function. So the way to do that is through the context. The data is in demand. You get the data instead of data being pushed through you, as you do with arguments, function arguments. It's an efficient alternative to passing arguments to functions, in fact. So instead of pushing lots of variables that the callee can take, you'll just pass in the context to some variables in your stack frame and make that available to other stack frames. Data can cross multiple stack frames and allows multiple contexts to be linked up. So here's the context, the simplified version of the context. What is the context? It is basically like a fusion map. You have the key, which is the ID. You have the data type, T. And you have a reference to the next context. And you have two variables here, which are references to a value and the reference to the next context. So basically, it's like an element of a fusion map. One context is like an element to a fusion map. And contexts can be linked together, like a linked list. So you have this context, which has this data and points to the next context, and so on and so forth until you have the empty context at the end. So searching goes this way. So it tries to search the first context with a same ID. If it has that, it returns successfully. If not, it will try the next context and then the next context. Interestingly, this is very efficient. You might think that it is a linear time operation, but it's not. Because of compiler optimizations, and I have code testing that, it's a 0-1 operation. So you get the value immediately because of compiler optimizations. So you have the empty context at the end. So as I mentioned, it's like a linked list of contexts. You have context 1, then context 2, pointing to context 3. At the very end, you have the empty context, which returns nothing. Here's an example. You have two contexts and the empty context. So all linked. The first context points to an integer. The second context points to a double. And the first context is specified by the ID foo. The next context is specified by the ID var. So if I want to get the context bar, I will get this part. And it's very fast. So here's an example of a context usage. Foo is calling bar. Here in foo, we set up a context, an integer, and then the context with the foo ID and the type int and pointing to the empty context as its next context. So there's only one element in that context. And then when it calls bar, it passes in that context. And then in bar, it accesses, it gets the context specified by the ID foo ID, using this guy over here. So as you can expect, the printout will be 1, 2, 3. Pardon? Oh, okay. Thanks. Okay, so here's the setting up of the context, and here's the accessing the context. So same ID, foo ID, and foo ID. And this int here, you pass a reference to that, this variable here, I. So the output of this one here will be 1, 2, 3. Is that clear enough? Okay. Question?
Why is it passed by reference? First argument.
This one? Which one?
I.
I. So it's always passed by, because you have the actual variables in a stack. And the context is actually just referencing that variable. Don't worry about the const reference. I promise you, it's very fast. I have a test for this one. Getting the variable here, compiler optimizes that very well, and you just get a constant. In this particular case, I will collapse to a constant. Okay, so to get the rules running, working, we need two parts: the rule definition and the rule itself. So these are new concepts introduced in Spirit X3. The first thing that I'm going to tackle is the rule definition. Rule definition is specified by an ID and the right-hand side. So it encapsulates the right-hand side in the class itself. So when you construct a rule definition, you need to pass it in the RHS, the right-hand side. And how does it do the actual parsing? This is important and quite tricky, in fact. What happens here is that before parsing the RHS, the right-hand side, it sets up a context which references the right-hand side parser. Okay? So this thing over here is specified there in this context. The reason is that the right-hand side, any node inside the right-hand side of the parser will have access to this context, the context of this rule definition. If you have an ID, if you know the ID of the rule, then you'll be able to get the right-hand side of the rule through the context. And then we have the rule. So this is a bit of a tricky part now, because the rule is empty, doesn't have any variables. But what does the parse function do? It tries to get the context, the right-hand side, in fact, from the context, because it knows the ID. And because it knows the ID, it's also able to have this operator overload here, which is a weird way to have an assignment operator. But this is done. It's a const. It doesn't do anything. It's an empty class anyway, so it can't do anything to mutate itself. Instead, it returns a rule definition. Because when you have this, when you're assigning the definition, to the rule, you have the definition there, and we will create a rule definition from that with the same ID as we have. Any questions so far? This might be too, am I going through too quickly? Yes?
The ID you make up yourself, right?
Yes.
Yes, if you use the ID twice, you get some kind of error message.
You can't, in fact. Okay, the question is, you supply the ID, but what if you have conflicting IDs? There will be a compile time error. You can't do that. So there will be a conflict. When you combine them together, there will be a conflict. Yes?
Just to be clear on the distinction between rule and rule definition. So now you have two separate classes, one that actually contains the parser logic, such as the proposition or terminals inside them, and one class, which is the rule, two references in other contexts. Is that what distinction?
Yes. So the question is, do we have the rule and the rule definition? What's the difference between the two? Did I get the question correctly? Okay. So the rule definition knows about the right-hand side. The rule itself does not. Because when you create a rule, you don't have a right-hand side yet. But when you have a rule and you assign a right-hand side parser expression, then what happens is that the rule here will create a rule definition and return that to you. You can capture that using auto. We'll see that later. So here's what's happening. So we have a rule. You don't have a right-hand side yet. You're just declaring the rule. Because it's recursive, you don't know the right-hand side yet. It has to follow later. AX is defined like we did before using auto. But this time, AX, you can have the rule as one of its parts there. Okay? Now, here's the tricky part. Here's the nice part here. Here's the start of the grammar. What this does is, this part over here, X is a rule, right? And it gets assigned the right-hand side, which is the parser expression that we're interested in. And when you assign it to X, it calls this member function. It calls this member function here, which returns a rule definition. And then, that rule definition, this one actually is a composite, which is a rule definition. And it gets captured by the start rule here. And that works. It works. So here's what's happening. When you call start, it will call the rule definition parse member function. And in the parse member function, it will set up a context which will point to this right-hand side specified by this ID. This is your ID. Okay, now it parses, it calls this one and this one. It calls, when it calls AX, it calls this rule here. When it's time to go to the X part of the sequence, the X part accesses the context specified by this ID, which is this one over here. And it calls it to parse. Yes, question.
Do you have a get parser function on the rule so you could do that in 2 lines?
Yeah, that'll be nice to have. And a lot more. The context is a very powerful mechanism, and there can be lots of helper functions for doing that. So yes, you're right. It will be a lot nicer if we have something like get rule with the ID and then the context. Is that what you're saying? So it'll be
In this
easier.
case, I was just thinking if you wrote x equal the rest of that expression, and then on the next line autocount start equal x dot get parser or something like that, you'd make it a little plainer what was happening instead of the odd double assignment.
Oh, okay. Let's discuss that offline. There can be lots of improvement to the interface, of course. Okay, so here's how I currently encapsulate the grammar. So we still have the grammar, but there are easier ways to create parsers. Here's one, based on our previous example, just using const objects. So I have a definition inside the namespace, and I hoist the grammar that I'm interested with, which is this one, pertaining to this one over here. So you can use this immediately as a parser. Okay, so looks like I'm on time. Or not. So I'll go through the walkthrough of Spirit X3, the actual code, so to get a more deeper, even deeper understanding of what we have in the actual code itself. Just examples here, so I won't go through all the details, but you can see the pattern. And this is actual code. This is not the toy anymore. This is actual code of X3 that you're seeing here. And most of the slides here fit in one page. So what I'm trying to say is that it's simple to understand. There are simple classes. There are one-shot classes. And this is an example. The simplest parser is the EPS parser. So same as before. Almost, but we added an attribute, which is quite important with Spirit, starting from Spirit v2. The attribute is the way to get the data from the parse. So here's what an EPS parser does. First order of business, try to skip spaces. And then what the EPS does is just returns true. Always parses true. So what's new here? The attribute. We'll get into that a little bit later. And the unused type. Yes, question?
Joel, you moving completely to an attribute-based parameter because there's no support for speech.
Okay, the question is, are we moving to a pure attribute-based parsing and no support for semantic actions? The answer is no. We'll still be supporting semantic actions using C++ 11 Lambda, and possibly still support, optionally, Phoenix. Okay. So attributes. All parsers expose an attribute specific to their type. For example, the int parser exposes an int. The car parser exposes a car. The clean star with an int as a subject exposes a stud vector of ints. The sequence int followed by a car is exposed with the attribute of a fusion DQ with an int and a car. This one and this one. Some parsers may have unused don't care attributes. One such example is the EPS parser, the one that we have a while ago. It doesn't have an attribute. That is why we have the unused type as the attribute. And you have this flag here specifying that, okay, this guy doesn't need any attributes, doesn't have attributes. So these are further examples of parsers with no attributes. Okay, so we've categorized attributes this way. So we have the unused attributes, the plain attribute, for example, int, car double. We have the container attribute, any kind of stud container. A tuple attribute, any kind of fusion conforming sequence. A variant attribute, a boost variant. The optional attribute, using boost optional. Yes, question?
So when you say any kind of fusion conforms to this,
You can supply your own, in fact. So I'll explain a little bit more later. There's what we call, and actually I'll explain in this slide. Your question will be explained in this slide. Okay, so here are the new attribute propagation rules. We have something similar in Spirit v2, but I tried to rationalize a bit more and to refine it a bit more. Unlike before, we have just a whole attribute propagation scheme. So I tried to categorize that into 3 parts. First is attribute synthesis. What is attribute synthesis? Attribute synthesis is when a parser needs to synthesize an attribute. If you've noticed the parse member functions a while ago, you'll see that you can pass in an attribute, okay? But you may or may, you need not supply an attribute. In fact, you can just pass in unused type. That way, you're asking the parser to synthesize the attribute itself. So for example, if this sequence is connected to a semantic action, and you don't have an attribute supplied, this parser will have to synthesize that attribute in order for it to be passed on to the semantic action. And by saying that, I guess I've given a hint to answer your question. So that's the attribute synthesis that we have. But we have here another set of attribute scheme, which is attribute compatibility. So because you can pass any type of attribute to your parser, it has to be able to know which is compatible or which is not. And it is defined by these rules. So for example, you might say that any kind of tuple can be passed on to this sequence parser here, right? As long as you have that A will have an attribute of T, and B will have an attribute of U. So any form of fusion sequence can be passed in instead of tuple. So for example, you can pass in a fusion list or struct of your own struct. This is adapted using the fusion adapt sequence, if you know such thing. So any type of fusion sequence you can pass in as long as the elements have this type. But it's more than that. Actually, with this rule here, with this attribute compatibility, we don't need the exact types as long as the type there is compatible with the types of the attribute types of the specific rules itself. So that may be a bit confusing. But there are attribute compatibility rules here that's specified in the documentation. So in this example, in this particular example, the sequence A followed by B can definitely take in a tuple. But it goes beyond that. It can also take in a vector, because the sequence A and B is compatible with a vector, stud vector, as long as one of these holds. As long as A has an attribute of T and B has an attribute of T as well. Or as long as A has an attribute of vector T and B has an attribute of T, and so on and so forth. So these are the rules. These are the compatibility rules. So these vectors are compatible with this sequence as long as these things hold. One of these things hold. And I also separated attribute collapsing. What is attribute collapsing? As you know, some parsers may have unused types. So for example, if A has a type T and B has an attribute type unused, the result will be collapse to just T. The unused part will be taken away. So same thing with this one. And if both A and B have unused attribute types, the result will be unused. So these are the rules for the sequence parser. Question?
So if A and B are synthesizing will that collapse to a flat tuple?
Yes. So this always holds. Oh, okay, sorry. Repeat the question. The question is, if A followed by B, the parser, the sequence parser, synthesizes a tuple with an unused type, will it be collapsed? Yes, the answer is yes. It will be collapsed.
Actually, I'm interested if A and B both synthesize tuples.
Oh,
Synthesize tuples. Will that be, will you end up with a few or a tuple with its own out?
it will be, the synthesized attribute will be a tuple of tuples for X3. With V2, it will be a flat tuple. Actually, I might be wrong. I have to look at the code. It might be a fusion iterator range. I might be wrong. I'll get back to you on that. Okay, here's a very nifty utility that we always use in Spirit. And in fact, it's also used in Fusion. And I stole the idea from tuples ignore. There's a small class there called swallow assign. So what does it do? It can take it any value at all and just throws it away. So it can take it any type, can assign to it. You can do that, but it doesn't do anything. It's an empty class. So it's like a sink, void sink. So it can't take it anything. So we use that a lot for specifying unused types, for example. Okay, so we're refining the context. We've had a brief introduction when we went into the Toy Spirit X3 parser. Here's the actual class that we have in the code base right now. So it's basically the same as before, a little bit more refined. The main difference between this and the toy is that we're using the unused type as the terminating context. So the unused type masquerades as a context in this case. To do that, we add these member functions inside the unused class. So it returns nothing. So if it doesn't care what ID you pass, it just returns nothing. So it's the terminating case. It's the end case. Okay, here's how the skip over looks like. Pretty simple. It just skips over. But what's interesting here is that we don't need to pass in the context. We don't need to pass in the attribute. It doesn't need it. So again, we are using the unused type here to specify that we don't care. We don't care about the context. We don't care about the attribute. We just care that you skip all the spaces. Okay, so here's another primitive parser, the EPS parser. Okay, we've had this before, right? The only thing that needs to be done is to have the EPS itself, the expression template that the user will use. So that's the EPS thing over here. Now, let's move on to an int parser. This is another primitive parser. And this is, again, this is part of the code base. So that's how it looks exactly. Quite simple. So we did our best to separate the main logic from the parser itself, the main logic of parsing. So why? Because our intention is for you to be able to use these simple utilities for parsing ints without having to, take in a whole bunch of expression templates and all that nice things. So if you want to have a very fast integer parsers, we have the extract int, which is the logic behind what's happening in the int parsers. Again, the expression template part. Now, here's the clean parser. Again, it fits in one slide, but except for I separated the logic for the parse itself to emphasize the point. Looks familiar, right? But there are a couple of things that we added. First, now it's inheriting from unary parser. So unary parser inherits from the base parser. So all unary parsers inherit from that. It's just a refactoring of the parser tree. So you have at the topmost the parser class, that's the base, and you have your unary parser, and you have binary parsers. That's it. Here's the unary parser. It inherits from the base parser class, and it has a subject, one subject. Constructor takes in that subject, and you have some type defs to to make it simple for and uniform across the whole parser hierarchy. So you'll expect that for all unary parsers. And here's the expression template for the clean parser. So I overloaded the operator star and take in a subject. And I return a clean, but before doing so, I need to convert whatever this is into a valid parser, if possible. Sometimes it's not possible. So the ask parser here tries to convert a type into a valid parser. So it's quite simple. So it returns the composite clean parser passing in the subject. First, it has to convert the parser, the subject into a valid parser. A little bit later, you'll see what happens if you try to pass in something that is not a parser. So that's where error handling comes in. So there you go. This is the crucial part here, the ask parser. And here's the ask parser definition. So we have the main template, which is empty. That's important. It's empty. And you have the function here that tries to convert any type of parser, any type of value, in fact, into a parser. There are specific cases, for example, the literal string or the literal character can be converted to a parser. It's not a parser. For example, quote X, single quote, that's a literal character. It's not a parser, but it can be converted to a parser because we have specializations for that. For the in-use type, we have specialization for that. Okay. We also have a specialization for anything that is already a parser. So anything that is derived from parser base will be converted, will be passed as is. So you have the derived here, and it passes it as is. So it's already a parser, in fact.
Parser base is the class that used to be just parsers with white template?
Yes. I didn't have that on a slide, but they have the parser base, which is a base class of the main parser template class. And the purpose of that is to have it easy to be recognized. Just anything that is derived from that is already a parser. So there are other ways to do that, but this is quite simple. Okay, so as I mentioned, there's also a specialization for literals. For a car, for example, as parser for a car returns, well, a literal car parser. Okay, so here's the clean star implementation. I guess I don't have to explain that. It parses as much as it can greedily. Okay, this I guess I have to explain a little bit because we have actually two overloads of the parse function for the clean. I'm a little bit running out of time, but I'll try my best. Okay, this one is for the case where okay, sorry. Okay, This one is for the case where the user passes in an attribute. So in this case, we call this utility, which is parses into a container. We'll see more about that a little bit later. And this is how you parse into a container. So you get in, try to get the attribute of the container type, and tries to call the parser to do its thing, and then calls pushback to stuff the value that this parser gets into the container. So it is assumed that attribute here is a container. Okay, where? This part? Okay. Could you please repeat? Yeah, okay, this is just for explanation. You'll see later that this is not actually what we are doing. This is the actual code. This is just, I'm just trying to explain what's happening when you parse one element in a clean star. So this is essentially what's happening. But we use traits, and you'll have here that we have customization points to get the container value, to initialize the value, and to push back into the attribute. This is where the fun stuff happens, where you have move and all this stuff. So unlike with Spirit V2, with X3, we always use move as much as we can. So here, it's not pushing back, it's doing the right thing. And it makes sense because you don't need the value anymore once you push back, right? Okay, so here's the sequence parser. We've seen this before. The only addition is that we're deriving from binary parser and we have the attributes. Essentially the same as before. So here's the binary parser. It's like the unary parser, but you have the left and right. And a bunch of some type defs and static consts there to make it uniform for all binary parsers. And here's the sequence expression template. Same as you have in the clean, but this time you have the left and right, and it's the right shift operator we're overloading. But the same as before, if you look at this, it's returning a sequence, but left and right, you don't know if these are parsers yet. So it tries to convert that into a parser. Take note of the value type though. This is important. So it returns a sequence. This thing here returns a sequence. Now that value type is important because it gets into action when you have invalid expressions. Because you have the parser type which is empty. Yes, question? Could you repeat that question again? The previous slide? This one? Okay. Oh. Yeah, sure. The question is, can we consider trailing return types instead of this thing over here, that syntax here? Yes, definitely we can. Okay, now, for invalid expressions, I mentioned a while ago that the default parser template is empty. And because of that, when you have a T that can't be converted to a parser, what I'm trying to say is that if you have a type T and there's no specializations for that, this main template will take into action. So because that's empty, Sphinai will make that expression invalid. For example, so here's your clean star, expression as parser, then value type. And then you try to type in not a parser with a clean star. So what's happening? Since we don't have a specialization for not a parser here, there will be no value type because the main specialization is empty. The main specialization is empty, doesn't have a value type. So because of Sphinai, we'll have something like that. So it will not be part of the overload set. So that operator simply does not exist for this expression over here. And you'll get the error message exactly there. It will point to that exact line and exactly that position. Same thing with the sequence. Because we're using as parser as value type for the left part and for the right part, if you have a sequence expression that is not a parser, you'll have the same error message. No match for operator in term, not a parser. That's the exact message that you'll get, and it's very clear. Okay, so here's the sequence parser implementation. For the sequence parser, it made sense to have it have two overloads. One for unused type attributes. Let me remind you that the parameter, the last parameter is always the attribute type. So once you pass in an unused type for the attribute, that means that you don't care about the attribute. This thing gets called. And this is the same as we have before in the toy example. In fact, exactly the same. And we have another overload for that. The case where we have the user passing in an attribute. So in that case, what we do is we call a utility function for parsing the sequence. But in this case, we're passing in the attribute category as well. Why is that? So the reason is that the sequence parser can take in an attribute of a tuple type. But at the same time, there's what we mentioned a while ago, that's what we call the attribute compatibility scheme, where the sequence parser can also take in a stud vector or any other a standard conforming sequence. So here's how we dispatch based on the type of the attribute. And here's the first example. For container attributes, this is what gets called. If we have a container attribute coming in from the sequence, here's what it does. It parses into the container. We're using the same utility as we have for the clean star. That's what happens here. For tuple types, this is a little bit more tricky, and I'll just go through this quite quickly. Unlike Spirit 2, with Spirit X3, it's always a binary parser or a unary parser. In V2, we flatten the parsers. For example, if you have a sequence A followed by B followed by C, it's actually flattened into a sequence with 3 elements, and that's held by a fusion sequence. But in this case, for simplicity and to make it very simple, we have only binary parsers and unary parsers. For that, the question here is that how do we handle attributes, because attributes are flat. So for example, you have A followed by B followed by C. That's a binary parser of a binary parser. And then the user passes in a tuple A, B, and C. For that, the trick is to partition the attribute into constituent parts. And this is what's being done here. So the partition itself is being done here, and then before it calls the left parser, it needs to get the right part of the tuple, and when it calls the right parser, it needs to call the right part of the tuple. What's relevant there? I know it's a little bit difficult to explain, but the following next slides will explain that a little bit more. Here's an expression. Here's a complex expression, sequence. We have 1, 2, 3, 4, 5. But you have only 2 valid attribute types. The rest have unused types. This thing here, that thing there, these are literals with no attributes. So the synthesized attribute for this parser here is a tuple int. Okay? Here's the expression tree for that expression. But now here's the tricky part. Here's your attribute. How do you pass that into that thing over there and this parser over here? So you have to understand first that these are binary parsers of binary parsers of binary parsers. So it's nested. So here's the outer nesting. That's the left-hand side, right-hand side. This is the second level pertaining to that part over there. And so on, so forth. So here's what's happened. When we partition, we parse this. This is the outermost level of the parse. This is the right-hand side. I'm sorry. This is the left-hand side, and this is the right-hand side. This has unused type. And this will be determined that this will have attribute of tuple int. So by partitioning, we use a fusion iterator range to get the relevant range pointing to this tuple, the attribute that's being passed in. And then the next recursion level, this is what happens. So this is the left-hand side, and this is the right-hand side. Just so happens that this will have an attribute of int, right? And this will have another attribute of int. So that will be partitioned into 2 iterator ranges, one pointing to this part and another pointing to that part. Yes, question?
What would happen if you split it into 2 groups? Do you propagate iterator ranges across group boundaries, or do you only propagate tuple?
Okay, the question. Do we propagate the iterator, partitioning of the iterators across rule boundaries? The answer is no.
Okay, the rule always is a tuple, and
Yes,
all groups get as a tuple.
exactly. Okay, So here's the last part of the iteration. Recursion. So the last part is that this will be a use type. So this will be passed to this parser here. And this parser will get an iterator range pointing to this int over here. So a single value iterator range. So it works. Sorry, that's not the last part. This is actually the last part. So the last part will be, this will be have an int pointing to that iterator range, again, partitioned from the original source tuple. This will have a use type. Well, same as before. Okay, so here's the alternative parser. Almost the same as before, so I don't have to go through this anymore, I think. Same ET, expression template. It's almost the same as before. Very familiar. Once you get to know at least one unary parser and at least one binary parser, you'll be able to write any types, any kind of binary and unary parsers, because the scheme is the same everywhere. And this is the actual implementation of the parse function for the alternative. I don't have time anymore, so I won't have to. I can't go through the details on how the alternative parser is implemented. So we'll have to fast forward a little bit. This is a little bit tricky to explain. So since I don't have any more time, if anyone is interested, just approach me, and I can go through the rest of the slides. Okay, so I have to go through this very quickly, but here's the rule definition, almost the same as before. In addition, we'll have the attributes, and we have a way to name. So it's almost the same as the toy example, with a little bit complexity here and there. Type defs, naming, etc. But essentially, it's the same. Here's the actual rule context. Because rules can have attributes now, we have a rule context that will have an attribute. Here's the rule definition, how it parses. It sets up a couple of contexts, a little bit more complex than before in our toy example, because it will have to set up multiple contexts. All these contexts are accessible from the nested parsers contained by this rule. Yeah, question?
Does make context involve memory allocation?
No, it's all stack-based. And it's very lean, and it's very efficient. I have an example CPP file that shows that optimizing the code amounts to having it a const. If you have something like in the example before, where I have a context int pointing to int, and it's taken in by reference, but in the end it'll all collapse to a const because of compiler optimizations. If you've used the Fusion map, it's quite similar to the Fusion map, and it's very efficient. I'm sorry, I wasn't able to repeat the question. Does make context allocate memory? Okay, the answer is no. Nowhere in the library will you see a memory allocation from the heap, except for what? The TST. Sorry, that's not entirely true. We have the symbol table, which has a ternary straight tree implementation, which allocates from the heat. But that's all. Okay, so finally we have the rule. So it's again the same as before with a little bit bits and pieces to make it more easier and manageable. Here's the same as what we had in the toy example, where you have the right-hand side being assigned to the rule definition, to create a rule definition. This is part of the rule. We've seen this before, so I don't need to explain. Okay, so finally, here's how the X3 calculator grammar looks like. So first you set up a couple of rules, name them. There's a bit of redundancy here, so anyone with good suggestions on how to minimize the verbosity, I'm all ears. But no macros, please. Here's the calculator grammar now. Almost the same as V2, but everything is auto. And then how do I compose that into a grammar? There's actually the grammar class. We didn't go into details with that, but essentially the grammar class is just a fusion map containing these guys over here. And that fusion map becomes its context. So anywhere inside the grammar, you can access any of these rules using its ID. Question?
Which is the start of the grammar? Which one?
The first one, always the first one. The question is, which is the start rule of the grammar? So the answer is, it's always the first one. So there you have it. This is the grammar class. I don't have time to go through this anymore. So if you're interested, I gladly explain the details to anyone. Just approach me. This is how the grammar itself. So it's quite simple. In fact, I just don't have the time to go to all these slides. There's a lot, and that's my mistake. Here's the grammar context, which gets the rule using the fusion map. So there's a hash key. I know that those of you who are using fusion map can recognize that. And there's your grammar context. So just using the @ key to get the rule from the elements, which is a fusion map. And if not, it passes on the query to the next context in line. There are some more that I have here, but unfortunately we don't have the time anymore. So if anyone is interested, I'd gladly walk through the rest of the slides. But for now, I have to end this talk. So anyway, thank you very much.